The PlayStation 3 was never just a gaming console, it was a fortress of proprietary silicon, a technological enigma that for nearly 2 decades stood as the Great Wall of emulation. When it launched in 2006, the industry looked at its architecture with a mixture of awe and terror. It wasn't just another machine, it was an ambitious attempt by Sony to dictate the future of computing. For years, the consensus among experts was unanimous. The PlayStation 3 was impossible to emulate on standard consumer hardware. Its heart, the Cell Broadband Engine, was a beast so complex and so alien to traditional PC architecture that it seemed destined to remain a black box, locking its library of legendary titles behind a wall of mathematical complexity that no home computer could ever hope to climb. Fast forward to the present day, and that impossible reality has been shattered. The $600 machine that once required a specialized supercomputer setup to mimic its functions now sees its software running on devices that fit in your pocket. This transition from a massive, power-hungry monolith to a mobile application is an engineering miracle. We are witnessing a moment in gaming history where the most difficult console to master has become accessible on mobile ARM architectures and portable powerhouses like the Steam Deck. This isn't just a minor technical achievement, it is a total collapse of the proprietary barriers Sony spent billions to build. The myth of the impossible has been dismantled by the RPCS3 team. These volunteer developers, once dismissed as hobbyists, have transformed themselves into the architects of the most sophisticated translation layer in gaming history. The journey of the RPCS3 project is a global saga of open source collaboration, bypassing the traditional gatekeeping of hardware manufacturers. It began in 2011 with a simple Hello World boot, a tiny flicker of life in a sea of code that many thought would lead to a dead end. Since that first spark, the timeline has been one of relentless victories. By 2024, the project reached a staggering milestone. Nearly every title in the massive PlayStation 3 library is now categorized as playable. This global effort has decentralized the power of hardware, ensuring that the legacy of an entire generation is no longer tied to the physical lifespan of specific hardware. Before we continue exploring this technical odyssey, subscribe to the channel and tell us in the comments where you are watching from. This connection between the community and the creators is what drives projects like this forward. The motivation behind this monumental task goes far deeper than playing games for free. It is a battle for digital preservation. As original PlayStation 3 hardware succumbs to the inevitable capacitor plague, failing Blu-ray drives, and the general decay of mid-2000s electronics, the need for a functional emulator has become a race against time. Without RPCS 3, masterpieces like Metal Gear Solid 4 or the original Demon's Souls would eventually vanish, relegated to decaying discs and unbootable consoles. Emulation has become the only viable way to save these cultural artifacts from permanent deletion. The RPCS3 team built a digital library for the future. They looked at a processor architecture so dense that even NASA researchers studied its potential. And they figured out how to translate those specialized instructions into a language that a modern smartphone understands. In this series, we will deconstruct the engineering miracle that allowed this to happen. We will explore how the most specialized supercomputer architecture of its era was broken down and reconstructed into a mobile-friendly format. This is a story of persistence over profit, of thousands of programmers refusing to accept the word impossible. We are entering a new era where hardware independence is becoming the standard, and it all started with a group of people who looked at Sony's Great Wall and decided they were going to climb it, one line of code at a time. The fortress has been breached, and what we found inside changed the way we look at gaming history forever. To understand the magnitude of what the RPCS3 team has achieved, one must first confront the titan known as the Cell Broadband Engine. In the mid-2000s, Sony was at the peak of its dominance, fueled by a level of corporate ambition that bordered on technical hubris. They did not want to build a standard computer, they wanted to dictate the future. The Cell was not just a gaming chip, it was a joint venture between Sony, Toshiba, and IBM in revolutionary high-performance computing. It was envisioned as a universal brain, but for the game developers who used it, the Cell was less of a brain and more of a labyrinthine puzzle. While competitors at Microsoft moved towards symmetrical multi-core designs for the Xbox 360, one that resembled the familiar path of personal computers, Sony chose a radical alien path. The Cell was an asymmetrical monster that created a massive architecture gap between the PlayStation 3 and everything else. There sat the Power Processing Element, or PPE, a general-purpose core that acted as the conductor. However, the real muscle lived in the 7 functional synergistic processing elements, the SPEs. These were not general-purpose cores. They were highly specialized math engines with their own isolated memory pools called local stores. These incredibly fast units created a rift. On a standard PC, a programmer could throw a task at the processor and expect it to be handled. On the Cell, you had to manually break that task into tiny pieces, feed them to the SPEs, and then manage the timing of when that data returned to the PPE. This was the developer's nightmare in its purest form. Think of it like a chef trying to cook a banquet where every ingredient is kept in a separate, locked box. The keys to those boxes are held by 7 different assistants who do not speak the same language as the head chef and will only perform one specific action, like chopping or boiling at a fixed speed. If the chef does not coordinate the assistants with absolute precision, the entire meal is ruined. For developers, this meant simple tasks on other platforms became Herculean engineering challenges. They had to micromanage memory transfers and synchronization at a level that most had never experienced. This complexity was a deliberate hardware moat. Sony intentionally created an environment that was difficult to master, effectively locking their ecosystem behind a wall of mathematical difficulty to discourage easy porting to rival consoles. During the early 2010s, the consensus among the tech community was that the PlayStation 3 was a black box that would never be successfully emulated. Experts believed you would need a consumer PC at least 100 times more powerful than the console itself just to simulate the complex dance between the PPE and the SPEs. The PlayStation 2's Emulation engine, the scale of the problem becomes clear. While the PlayStation 2 was difficult to program for, it still operated on principles that felt like an evolution of existing ideas. The Cell, however, was a total rethinking of how software interacts with silicon. It was a machine that required developers to work to the metal in a way that modern high-level programming had abandoned. This created a dire situation for the future of gaming. Thousands of exclusive titles were effectively trapped on this proprietary island. Games like Metal Gear Solid 4 and The Last of Us were built specifically to exploit the weird, specific strengths of the SPEs, making them impossible to move to other systems without a ground-up remake. This set the stakes for the RPCS3 project. As original hardware continues to fail due to the inevitable capacitor plague, the library of the PlayStation 3 faces a slow extinction. The complexity that Sony built as a competitive advantage became a cage for its own legacy. The struggle to break the code of the Cell wasn't just about curiosity, it was a desperate rescue mission for a generation of digital art that was never meant to leave its original home. The early days of the RPCS3 project, beginning around 2011, were far from the polished experience seen today. It started as a humble experiment, a way for developers like DH and Hycom to see if the PlayStation 3's architecture could even be understood by standard PC hardware. At its inception, the project could only handle simple homebrew applications, basic programs that didn't even touch the complex 3D rendering capabilities of the console. The development team was venturing into uncharted territory, essentially attempting to build a high-performance engine while the car was still moving at full speed across a digital void. When the team first attempted to boot commercial games, the results were underwhelming. There were no epic cinematic openings. There were only scrolling lines of text, hexadecimal errors, and the occasional flicker of a black screen. It was a silent struggle against an invisible wall of code. The core technical hurdle was the translation. The PlayStation 3 operated on a specialized PowerPC architecture, while the computers meant to emulate it ran on x86 or ARM. This wasn't a simple case of remapping buttons. It required a real-time translation of the PS3's specific language into something a modern computer could execute without catastrophic lag. Imagine trying to translate a complex epic poem from an ancient dialect into modern slang while maintaining the exact rhythm and weight of every single syllable. Every instruction sent to the PPE and those 7 volatile SPEs had to be intercepted, decoded, and re-encoded on the fly. A major turning point arrived with the integration of the LLVM compiler. Before this, the emulator acted primarily as an interpreter, reading code line by line, which was a painfully slow process. LLVM allowed the RPCS3 team to implement a dynamic recompiler. This system could pre-compile large chunks of game code into a format the host processor could handle natively. It was like giving the computer a translated guidebook rather than making it look up every word in a dictionary. This optimization significantly reduced the CPU overhead, making it possible for games to finally move beyond a crawl and into actual fluid motion. While the CPU was being tamed, the graphics pipeline faced its own revolution with the arrival of the Vulkan graphics API. Before Vulkan, emulators were choked by the heavy overhead of older systems like OpenGL, which added layers of abstraction. Vulkan changed the game by providing to-the-metal access. This mirrored how the PlayStation 3 originally functioned, allowing developers to bypass traditional driver bottlenecks and communicate more directly with the GPU. The impact was immediate. Visual glitches that had plagued the project for years began to vanish, and frame rates began to climb into stable double digits for the first time. The project's growth followed the logic of the ship of Theseus. Because RPCS3 was open source, it wasn't the work of just a few individuals, but a global community. Thousands of contributors began fixing tiny, specific bugs within individual games. One developer might spend weeks fixing water reflections in a racing game, while another focused on audio synchronization in a niche RPG. Piece by piece, the original codebase was replaced and refined until the foundation was unrecognizable, replaced by a more robust and efficient architecture. This decentralization of development ensured that no single point of failure could halt the project, allowing it to evolve like a living organism. This effort culminated in the legendary Demon's Souls moment in 2017, when the game reached a stable 30 frames per second. It was the definitive proof that the impossible was now merely a matter of time. Demon's Souls, synonymous with the console's identity, was finally playable on a PC. However, the victory was not yet universal. Titles like The Last of Us remained elusive. These games utilized the SPEs in such specific ways that they would crash the emulator for years. Every crash provided a crucial piece of data that refined the translation layer, pushing developers to dive deeper into Sony's silicon maze, slowly chipping away at the final barriers. The landscape of emulation shifted dramatically once the RPCS3 team moved beyond the pursuit of mere compatibility and toward the goal of efficiency. For years, the project was synonymous with the need for high-end, power-hungry hardware. If you wanted to play a PlayStation 3 game on your computer, you needed a machine costing upwards of $3,000, equipped with the latest multi-core processors. However, the last few years have witnessed a paradigm shift, the transition from high-end desktop dominance to the era of the $400 handheld. This wasn't just a decrease in price, it was a fundamental change in how the complexity of the cell was handled by modern silicon. The narrative was no longer about whether a PC could do it, but how small that computer could get. The primary catalyst for this revolution was the rise of the Steam Deck. This device became the ultimate testbed for portable PlayStation 3 gaming, bridging the gap between desktop power and mobile convenience. It proved that the massive computational requirements of the Cell Broadband Engine could be squeezed into a mobile-class power envelope of 15 to 25 watts. Watching titles like Demon's Souls or Ratchet & Clank run on a battery-powered device was a wake-up call to the entire industry. It demonstrated that the RPCS3 architecture had become lean enough to function without a constant tether to a wall outlet. This success on the Steam Deck signaled that the impossible was now becoming portable, challenging the assumption that only high-wattage desktop CPUs could handle the PlayStation 3's intricate thread scheduling. This breakthrough was driven by what can only be described as optimization sorcery. One of the most significant technical hurdles in this process is the stuttering caused by shader compilation. To combat this, the RPCS3 team refined techniques like shader caching, which allows the emulator to preload visual effects so the GPU doesn't have to calculate them on the fly. Even more impressive was the implementation of SPU block rewriting. This technique allowed the emulator to reorganize the way it handled the PlayStation 3's unique synergistic processing elements, making the workload much more palatable for standard mobile CPUs. These weren't just minor tweaks, they were structural overhauls that effectively taught a modern processor how to pretend it was a specialized supercomputer without breaking a sweat. The frontier expanded even further with the arrival of high-performance ARM architecture. For a long time, the world of computing was divided between x86 architecture and the ARM architecture found in mobile phones. The gap between them once seemed insurmountable in terms of performance. However, with the introduction of Apple's M-series chips and high-end Qualcomm Snapdragon processors, that gap effectively vanished. The RPCS3 team began to bridge this divide, porting their work to systems that use entirely different instruction sets. The result is the emergence of the Pocket PS3. Recent footage of top-tier Android smartphones running iconic PlayStation 3 titles is more than just a tech demo. The idea that a device that fits in a pocket could outmatch the Great Wall of Sony's proprietary silicon is a testament to the speed of mobile technological evolution. This newfound portability has had a profound impact on the industry, specifically putting pressure on Sony. The existence of RPCS3 on handhelds raises a pointed question. If a group of dedicated volunteers can make these games run on a phone, why hasn't Sony offered a native backward compatibility solution for the PlayStation 5? While Sony has leaned into cloud streaming, which often suffers from latency, the RPCS3 project proves that local, high-quality emulation is possible on modern consumer hardware. This disparity highlights a growing tension between corporate profit models and the technical reality of what modern chips can actually achieve. Ultimately, the mobile barrier being broken is a massive victory for digital preservation. It ensures that the thousands of games trapped on dying PlayStation 3 consoles are no longer tied to a specific piece of failing hardware. Instead, they have been archived and liberated, made playable on virtually any modern computing platform. The library of the PlayStation 3 has become hardware independent. This transition ensures that even as original consoles succumb to the capacitor plague, the art they contained will remain accessible. The fortress of the Cell has not just been breached. Its walls have been repurposed to build a bridge into a future where gaming history is portable and permanent. The success of the RPCS3 team signals more than a technical triumph. It represents the end of the era where hardware dictated the survival of software. We are moving toward a future of hardware independence, where the very concept of a console generation is being fundamentally redefined. Historically, video games were inextricably linked to the physical boxes they were designed for. When the hardware died, the games often died with it. The PlayStation 3, with its proprietary Cell architecture, was perhaps the most extreme example of this hardware-locked philosophy. It was a fortress built to be unique, making porting or preserving its library a monumental task that many experts deemed impossible. However, the persistence of the RPCS3 project has demonstrated that no proprietary chain is permanent. In this shifting landscape, a console is no longer a specific box under the television. It is becoming a service or a sophisticated piece of software that can run on any sufficiently powerful screen, from a desktop monitor to a smartphone. This shift has profound implications for the next frontiers of emulation. The lessons learned from the struggle to master the Cell processor are now accelerating the development of emulators for more modern systems, such as the PlayStation 4. Unlike the eccentric and asymmetrical design of the PlayStation 3, the PlayStation 4 and its successor, the PlayStation 5, were built on standard x86 architectures similar to those found in high-end personal computers. Because the RPCS3 team spent over a decade reverse engineering Sony's complex operating systems and memory management, newer projects like Shad PS4 are reaching milestones in months that took years for previous generations to achieve. The grueling long siege of the PlayStation 3 served as a masterclass in software translation, creating a roadmap that makes the dismantling of newer, more standard hardware architectures a significantly faster process. The difficulty of the past has essentially paved a high-speed highway for the future of digital preservation. This technological progress also forces a confrontation with the legal and ethical dimensions of digital media. For years, the gaming industry has framed emulation primarily through the lens of piracy, viewing it as a threat to profit margins and corporate control. Yet, as the capacitor plague and failing Blu-ray drives begin to claim original PlayStation 3 units at an increasing rate, the ethical argument for emulation as a tool for digital preservation has become undeniable. Without the work of global volunteers, iconic cultural artifacts would simply vanish when a corporation decides they are no longer worth the cost of server maintenance or physical manufacturing. The RPCS3 project highlights a critical perspective, that software preservation is a form of archiving that should not be gatekept by corporate negligence. This tension between ownership and access continues to shape how we view the history of the medium, positioning emulators as essential libraries that protect our collective digital heritage. We are also fast approaching what experts call the silicon ceiling. As mobile chips and standard consumer processors continue to evolve, they are beginning to surpass the original power of the PlayStation 3 by factors of 10 or even 100. We are reaching a point where perfect emulation, characterized by zero bugs and total stability, is becoming the baseline expectation. This isn't just about reaching original performance levels, it's about surpassing them. The integration of artificial intelligence is the next transformative step in this journey. By incorporating AI-driven upscaling technologies like DLSS or FSR directly into the emulator, the community is transforming 720p titles from 2006 into experiences that rival modern 4K releases. These AI tools allow for the restoration of textures and the smoothing of frame rates in ways the original developers could only dream of, effectively future-proofing these games for high-resolution displays that haven't even been invented yet. Ultimately, the survival of this movement depends on the role of open source development. Unlike proprietary software, which is inherently fragile and subject to the stability or interest of a single company, the RPCS3 project is a decentralized endeavor. Because the source code is public and accessible, it belongs to the global community rather than a boardroom. It cannot be deleted by a corporate merger or a shift in market strategy. This openness has allowed the project to evolve like a living organism, incorporating bug fixes and optimizations from thousands of different contributors over the years. This collective effort ensures that the work done to break the Cell's proprietary chains will benefit future generations of gamers. It reinforces the idea that while hardware is temporary and prone to failure, the software that defines our gaming history can be made permanent through human persistence and shared knowledge. As we move closer to a state of total hardware independence, the walls of the PlayStation 3 fortress have been replaced by a bridge to an eternal digital library. The journey of the RPCS3 project represents a pivotal transformation in how we perceive technological limits. What started as a decentralized experiment in 2011 has fundamentally dismantled the myth that the PlayStation 3 was an untouchable fortress. This arc serves as a testament to the power of collective human intelligence over proprietary corporate engineering. We have moved from a time when booting a commercial PS3 title on a PC was laughed at to an era where high-definition emulation is the gold standard for experiencing these classics. The industry had accepted that the Cell processor was too alien to ever be translated effectively. The RPCS3 team proved that with enough time, data, and persistence, even the most complex silicon architecture can be replicated in code. This achievement is best understood through a final, striking contrast. In 2006, the original PlayStation 3 Fat model was a $600 behemoth. It was a heavy, loud, and power-hungry machine that required significant physical space to keep its complex processors from melting. It was a physical manifestation of Sony's mid-2000s ambition. Fast forward to the present, and that same revolutionary code is running silently on a modern smartphone. The power that once required a specialized supercomputer and a massive power brick now fits comfortably in a pocket, running on a battery-powered device. The roaring fans and spinning Blu-ray drives have been replaced by silent transistors and lightning-fast flash memory. This evolution marks the moment when the software finally outlived the hardware that was supposed to be its permanent home. We are witnessing the birth of the Netflix of history. The labor of the RPCS3 community is leading us toward a world where every game ever made is accessible at all times, regardless of its original manufacturer. In this new paradigm, gaming history is no longer a collection of fragile plastic discs and dying capacitors. It is a global digital library. This preservation ensures that titles like Metal Gear Solid 4 or Demon's Souls are not lost to the march of time. They have been archived and liberated from the hardware-locked cycles that once threatened to turn them into digital ghosts. Because of this movement, the art of the PlayStation 3 era will remain vibrant and playable for decades to come, independent of whatever physical box sits under the television. None of this would have been possible without the human element. The RPCS3 project was not a corporate mandate. mandate. It was a labor of love, fueled by thousands of hours of unpaid labor by the RPCS3 team and global contributors. These developers chose to spend their nights reverse engineering proprietary drivers because they care about the medium. This project proves that while corporate entities might move on to the next generation to drive sales, it is the community that remains the true steward of gaming culture. The fortress of the Cell didn't fall to a battering ram of superior hardware. It fell to the persistence of thousands of programmers who refused to take impossible for an answer. As we stand at the end of this 20-year saga, one final question remains for the players. If you had the chance to carry the entire PlayStation 3 library in your pocket today, which game would you boot up first? Would it be the cold corridors of the original Demon's Souls, or the cinematic journey of The Last of Us? The choice is now yours, no longer dictated by the availability of aging consoles. In our next deep dive, we explore the original sin of Sony's hardware, the PlayStation 2's Emulation engine. We will investigate why that architecture was even more difficult to crack than the Cell. Until then, remember that the only true barrier to preservation is the belief that it cannot be done. This concludes our journey through the impossible. Thank you for joining us on this historical technical odyssey into the heart of emulation. The future of gaming is no longer locked behind the walls of the past. It is alive in our hands now.